Welcome back to what I hope is the last video. This will be the last material before fall break. So we're going to wrap up our talk about experiments. So we already talked about the 4 principles of a well-designed experiment, and we kind of included a 5th, which was blocking. But in general, these are the important pieces. So if you were asked to design an experiment, you would have to establish most or all of these things. And really, we're just covering our bases here. Any one of these, or multiple, could be part of an AP exam question or a test question for this class. So, just to review, it's important what your response variable or variables is or are. What is it you're looking for in this experiment? What are you trying to figure out? How are those response variables measured? The factors of the experiment. What are they? How many of them are they? Is this a 1-factor experiment, or are there multiple factors? And how many levels does each of those factors have? Maybe one factor has 3 levels, but another one has 4, another one has 2. You need to determine that if you're in charge of designing the experiment. How are the treatments going to be assigned? Yes, it's random, but that is probably where most of your explanation is going to be. Are you using a random number generator? Are you using a random number table? How is it that you're going to turn these individuals and these treatments into an actual experiment? Is there a control group? There probably should be. That's one of the principles of a well-designed experiment. But what does the treatment look like for the control group in the context of your experiment? They are still getting a treatment. Perhaps it's a placebo that has no real effect. Right? Blinding. Is there blinding in this experiment? Is it possible for it to be double blind, where neither the experimental units nor the people providing the treatments know which EUs are getting which treatments? Is it only single blind? Or is it not possible to blind at all, or maybe it's just not a good idea? And the idea of blocking. You need to block if there are any variables that you feel would really impact the results of the experiment, but you can't control for them. Remember in our example from the last video, the age of the people in the experiment, we can't control for that. We can't just be like, and you get to be 30 years old, right? So we have to block and randomize the treatments within each block. Then we can compare the results between the blocks at the end. So, there's a lot going on in experiments, but you'll be expected to be able to design your own experiment. You have to think about these things. Don't worry too much about getting everything perfectly right. As long as you get the general idea, you're probably going to get many of these without really thinking about it too hard. Okay, so don't worry too much about that. Okay, so to kind of wrap up our experiment talk, I've got an example from our textbook, and I will bring it up now. Please work. Hey, there it is. There's the example. So, let's say, well, can special study courses actually help raise SAT scores? One organization says the 30 students they tutored achieved an average gain of 60 points when they retook the test. This happens a lot, especially during school years. Like, maybe it's just because of who I am and what I do for a living, but I hear all the time about these places where you can send your student and they will improve on these standardized tests like the SAT. It's like magic. Part A asks, explain why this does not necessarily prove that the special course caused the scores to go up. I'm hoping that you have an answer in your head for part A. If you could, just pause the video for a few seconds. You don't have to write out your response, although you could, but at least think about it. Why can we not just assume the course caused the grades to go up? Okay, let's see here. Why can we not just claim that the course is improving the scores? Well, we're not accounting for any of those lurking variables, are we? This certainly wasn't an experiment. I don't even think you could necessarily say it's an observational study with the information that you're given here. So it could be that students who enroll in courses for SAT prep are already more likely to improve their score, even if they don't actually take the course. Maybe they go and they just sleep the whole time. Students who enroll in courses like that, whether it's because they want to or whether it's because their parents are making them do it, those students are probably more likely to improve the second time they take the test than students who would not enroll in the course in the first place. That's just one lurking variable that could really be masking what's going on here. There could be many others, but that's the main idea. Part B, now's your chance. Propose a design for an experiment that could test the effectiveness of the tutorial course. So design your own experiment such that if you got certain results, you could prove a cause and effect relationship. Go ahead and try that out. At least think about it for a few seconds. If you can write that down, that would be great practice for homework, tests, and the AP test. Sorry, I had to move the problem over here to show my answer. This requires quite a bit of writing. I'm not saying that my response here is perfect. I probably didn't hit all of these points, but I think this would be a good enough response to get an essentially correct if this question were asked on the AP test. Gather 30 student volunteers. I chose 30 because that's how many they used in the prompt. You can use however many you think is reasonable. Using a random number generator, produce a unique sequence of 15 numbers between 1 and 30. There are different ways you could do this. Each student is assigned a number in this range, and the 15 numbers chosen here represent the 15 students who will attend the study course. The other 15 students do not take the course. So, those are your two treatments, those who do and those who don't. I didn't draw a diagram of what this looks like, but you could in addition to your written work. All students will take the SAT before and after the course. So for the students who didn't take it, they just take the SAT, wait a little bit, take it again. The students who take the course, course, SAT. We're going to calculate the scored differences, after minus before, for each group, well, for each student, I guess I should say. And we're going to compare the mean differences between the groups. What we would expect to see is that the group of students who took the course, that difference should be bigger than the group of students who didn't. If those differences are large enough between the two groups, then we might be able to say that the study course is actually effective. Okay? You'll notice a decent chunk of this design is explaining how the randomization of treatments occurs. There's really not much outside of that, really. Choosing how many individuals there are, that's a part of it. But really, from here until here is the randomization of treatments. It's most of the response. Okay. And many students leave out the part where you actually say what you're going to be doing. Like this thing here, the response variable. What is it that we're really interested in finding out? It's if their score's improved. How are we going to measure that? By doing it before and after. It's pretty standard. So that's part B. Let's talk C. Suppose you suspect the tutorial course might be more helpful for students whose initial scores were particularly low. How would this affect your proposed design? So, for example, a student who scored like a 500 on the SAT has a lot more room to improve than a student who scores a 1500. Because the maximum is 1600. Okay, so maybe we want to, for some reason, because of this, we want to account for that somehow. Can we tweak this design easily to account for something like that? I don't think so. First of all, because as this is done, like, we don't know who those students are beforehand. Them taking the SAT the first time happens after the study starts. But I'm thinking, if this is a variable that we cannot account for in the study, we need to do this. We need to incorporate some type of blocking. So maybe describe how you would block the students and how does that really affect this design? Okay, so in my limited room that I had up here that I ran out of, I thought the best way to show how the design would be effective would be to just draw the diagram. So we're going to be blocking on the initial score of the test. So we've got our 30 students. Let's say they take the initial test. We're going to block them. The top 10 scoring students will be in their own group. The middle 10 students who scored it in the middle will be in their own group, and the lowest 10 students' scores will go in the bottom group. Within each of these score categories, we're going to randomly assign the 2 treatments. 5 of those 10 are going to take the course, the SAT prep course, the other 5 won't. So we are assigning both treatments to all 3 of these blocks. And then some will take the course, some won't. We'll compare the results within each block, and then we'll compare results between the blocks to see, one, if there's a difference in any of the blocks individually, but then also if there are differences between the blocks as well. And if that seems complicated, there are entire graduate level statistics courses about how to do this correctly and how to actually compare these results in all these different ways. It's ridiculous how much detail you can go into to make sure this is done accurately. But for now, I think just being able to say you're blocking on initial score and showing what that might look like, that would be great if you could do that. All right, so now you are an experiment master. You can design an experiment with the best of them. I believe that. So let's get into some interesting questions about experiments. This is really where the rubber meets the road. So suppose we do the caffeine experiment. And it's conducted appropriately. Okay, so we've followed all the principles of a well-designed experiment. Everything is on the up and up. The Coke group had a pulse rate increase 1.2 beats per minute higher than the caffeine-free Coke group. That's kind of what we would have expected to see. Does this mean that caffeine increases pulse rate? It's the whole point of doing the experiment, right? We want to be able to answer this question. So we designed the experiment appropriately. These are the results we got. Can we answer this question? Yes. Well, if you say yes, how small of a difference are you willing to tolerate to still say yes? If this number were 0.1, would you still say yes? If your answer is no here, how big does this number have to be before you change your mind? Is 2 beats per minute higher enough? Or does it have to be 3? Or 5? Or 10? Or 50? Where's the cutoff? It's an interesting question, isn't it? And as of right now, I don't think you're well equipped to truly answer this, because it's much more nuanced than a layperson might suspect. So we performed this experiment, right? We conducted it appropriately. We had a certain group of volunteers who agreed to come in, be part of our experiment. Let's say we did the exact same experiment again. Would we get the same results? It would be remarkable if we did. Chances are the results would be different. How much different? Hard to say unless we actually did it more than once, right? The fact that the results of the experiment can be different depending on the volunteers we use, that's what we call sampling variability. It's the fact that the results are specific to the sample that we have. So in general, sampling variability is the notion that if you repeat an experiment, or this actually applies to surveys and observational studies as well, if you repeat it with different individuals, you will likely get different results. How different of results could you get? It depends on the context. It depends on your variables. It depends on the individuals you're looking at, the population, all of those things. You can get some sense of how much sampling variability you might see based on the individuals in the original experiment or observational study. So each person, each volunteer, had an after minus a before pulse rate difference. We can look at how those differences change among all the individuals that we looked at here. That might give us an idea of how much variability there could be if we did it again. But in general, we want to make sure that the result here is not just because of the individuals that we chose. We don't want it to be the case where we say, yes, caffeine increases pulse rate, but then someone else goes and does our same experiment and figures out that there is no increase, or there might even be a decrease between those two groups. We want it to be relatively certain that this relationship exists. Not necessarily that it's 1.2, but that it is an increase. So it'd be nice if we could put some words to this, yeah? There's nothing wrong with sampling variability. It's just the nature of statistics. If you do an experiment twice with different individuals, you're most likely going to get different results. That variability is what prevents us from concluding that any experiment shows is a cause and effect relationship. We can't just say yes to this, because this number might not track with the entire population. It may only be the case because of the people from this experiment. What we want to be able to show a cause and effect relationship is that the results are what we call statistically significant. And that means that the results have to be so clear that it's unlikely to have been produced by chance. Or in this case, from specifically the individuals that we used from that sample. Okay, we want this number to be large enough that we're pretty sure if we did it again with different individuals, we would still see an increase. How large does that number have to be? Well, stay tuned, because a decent chunk of the second semester of this course is going to be devoted to answering questions like that. That's one of the major things that you're going to learn in this class is what does it mean for results to be statistically significant? So all you're getting right now is the big picture view. Statistically significant results are ones that are not produced by chance. We are relatively confident that this is a relationship that exists. And for us to say that, our results have to be pretty clear. Okay, only then can we conclude that there is a cause and effect relationship. I want to make it clear that you could have a giant number here, and the results could still not be statistically significant, because you can only determine statistical significance in an experiment if the treatments are assigned randomly to the experimental units. So if you skip that step and you just say, just pick what drink you want, no matter how large of a difference in pulse rates you see between the groups, you would not be able to conclude a cause and effect relationship. And really, that's the whole point here. If you find out that the results are statistically significant, which we will determine eventually, then you can conclude a cause and effect relationship. Then and only then. You need statistically significant results. You need to see a clear pattern there, a clear number that shows that increase before you can conclude a cause and effect relationship. Okay. So maybe something about this experiment has been bothering you this whole time. This experiment used volunteers from the very beginning. We didn't take a random sample. Is that a problem? You may remember, potentially, that you're not going to be able to take a random sample for every experiment. I used the example of if you're trying to test whether a drug to fight cancer is effective, you can't just take a random sample of individuals. They have to be suffering from that specific type of cancer. It's going to be people from hospitals. So, to a certain extent, a random sample isn't even possible for most experiments, many experiments. Is that a problem? No. As long as you're randomly assigning the treatments, then you can determine statistical significance, potentially, and conclude a cause and effect relationship. But if you're using volunteers and not a random sample, it does prevent you from something else. If you're taking volunteers for your experiment, you can still conclude cause and effect as long as the treatments are assigned randomly. But you can't generalize the results to a larger population. So for our experiment here, we wouldn't be able to say, oh, caffeine increases pulse rate for everyone. We would only be able to say it for people like the ones that we looked at. So maybe among people who would volunteer for that study in that location at that time, like, you can't generalize if you're taking volunteers. If you want to be able to say something about a large population, you have to have taken a random sample. But that doesn't mean that you can't do an experiment with volunteers. You could still conclude a cause and effect relationship, but that relationship may not apply to a larger population unless you take a random sample. So just to recap what we were just talking about here, random assignment of treatments for an experiment, that is what allows you to conclude cause and effect relationships if the results are statistically significant, which you don't know how to determine quite yet. Random sampling of the experimental units is what allows you to generalize the results to a larger population. And that's actually the case for experiments, surveys, observational studies, pretty much everything. That's why random sampling was so important for these as well. So really only if you do both of these things can you say, yes, caffeine increases pulse rate in general. But many experiments out there, especially in the medical field, they can't say this necessarily. So what they do is they publish the statistically significant results, but just say, hey, it worked for our sample. Your mileage may vary, because that's all they can say. Okay? It turns out it's really hard to get both of these in an experiment. But that's still pretty good. So, that is all the material of Unit 3. We're pretty much up to fall break. Make sure you work on the progress checks for Unit 3. You should be able to do all of those problems now. Your unit test was coming up before fall break. If you're behind, don't worry. Maybe you can use some of that break in that week to get a little bit more caught up. You really should take this unit test. I'm really hoping that you can get these assignments and assessments finished before we start back up after fall break with Unit 4. Hopefully, the rest of instruction this year will take place in person. That's what I'm hoping for. Thank you for sticking around for these videos. I really appreciate it, and I hope you learned quite a bit in this first quarter of the year. But we'll see you in class next time.